Let's start with the simplest case. It's called one sample t-test. And the idea is very similar to what we have used by calculating confidence interval for average of one sample. Okay. So in one sample t-test, we will use t-distribution to find this chance. We know that average values for samples are distributed normally, but if you don't know the parameters of population, you need to use a t-distribution. And then we will talk only about one sample so far, so we don't have to compare the samples. In this case, we have the following possible null hypothesis: that the average of population is equal to given, if equal or below given, or it's above given, right? That's another example with all these males from Olberg. So the simplest hypothesis will be if we compare the parameter with the particular fixed value. It's very rarely when you use it for average values. Usually you test either that it does not exceed or it's smaller or equal than given. But let's start with this one, because I think it's easier to understand how it works. So that's our null hypothesis. And then we have alternative hypothesis, which means that simply mu does not equal to 175. Okay. Then the same example. We took a random sample, 20 adult male persons randomly selected from all others in Olberg, and then we got these statistics. How likely we can get this statistic, or even worse, we will discuss what even worse, if the null hypothesis is true. So let's see how to calculate it. Well, we know that we need to use a t-distribution. We know that the average, okay, can be calculated. The average of the population depends on the sample average, and then we have this t-value and standard error, right? For a given certainty, okay. The idea is, you remember what t-value equal to. Well, we calculated t-value using t-distribution for different degrees of freedom, okay. Now we don't need to estimate mu. We know it, okay. So we know mu, we know m, we know s, and we know n. But now we don't know t. What will be t in this case? Let me show you a couple of formulas. So this is how we calculate confidence interval for the mu. But if we know mu, we can calculate t, which will tell us the following. Look at this. So here in denominator here, we have a difference of means. How far is m from mu, right? Okay. Then what do we have in denominator? We have a standard error. What is a standard error? Standard error is a simple thing. It's a standard deviation for your m values, okay? It tells you how far it can go from the mu. So this operation is actually a standardization. The t-value will be how many standard errors your average value of your sample is from assumption, from average value of the population, okay? And then depending on degrees of freedom, you can estimate how extreme this t-value is, okay? So once again, you can compare this with the standardization. You remember, in normal distribution, we use this operation standardization where we standardize the values, right? So instead of x, instead of the values, we got z. Z was the z-score. It tells you how many standard deviations your x value is distanced from the average. Here we have actually the same. Instead of x, we have m, it's sample statistics. We still have mu, so it's a distance between m and mu. And this is nothing else but standard deviation of your mu values, right? Here it was standard deviation of x, and here we have standard deviation of m. So in this case, we do standardization. So t will be how many standard errors our average value of our sample is distanced from the average value of the population. Okay, so we can call it a standard score or a t-score in this case. Now look, this is the distribution. Okay, so this case where t-value is equal to 0, it's m equal to mu. Okay, so this is the most likely case for us. Okay, and then for example, we calculated t-value and we got, let's say, we got exactly m equal to mu. In this case, we don't have any doubts, right? So it's very likely that this sample came from this population, because we already have average of sample is equal to the average of the population. What if it's 1? Well, you see, it's one standard error far from this case, okay? So it means that it's a bit more extreme. The far you go from the center, the more extreme the case is, right? Or for example, if you have -1, so it means that your average value is below mu by one standard error. So it's equally extreme, right? But in this case, the distance will be the same. So the extremeness of the sample will be the same in this case, right? Then it's the same for 2 standard errors, and then we can just continue. So the more far your sample is from the mu in terms of standard errors, the more extreme, the less likely the sample came from this population. Okay. Now look, let's get back to the example with the height values. Let's say this is our null hypothesis and this is our sample size, right? So how to calculate the t-value? Let's say we took a sample and this is our sample statistics. Okay, so this is standard deviation and this is average. In this case, the t-value can be calculated simply by taking the difference between m and mu and then taking a standard error. So this is our t-value here. Okay, where it is located? It's here. So it's minus 0.5. It's pretty close. It's pretty close to this case, right? So it's not that extreme. It's not very extreme. What if we have another sample, and in this case we got 177 as average of the sample and standard deviation is 8? Well, in this case t is equal to 1, so it means it will be here. And the distance is a bit larger, so it's a little bit more extreme. But still, you can see that it is within the area of most common values, right? Now let's say we have more extreme case. We took a sample and then this is the average and this is the standard deviation of the sample. In this case, the t-value will be minus 3. And so minus 3 is here. And you can see that the distance is pretty large. How likely we can get this value if indeed the null hypothesis is true? Well, it seems not very likely, but we can calculate the probability for that. Okay. Now think. We remember this when we calculated confidence intervals, we use this most common values, the most expected values, right? So we have, for example, if we are talking about 95% of the cases, so if we use confidence level equal to 95%, we can say that these values, these t-values, are the most probable ones, right? These are too extreme, and these are too extreme, because it means that the sample will be the sample average will be too large to the population, and the sample average here it will be too small comparing to the population. It's still possible. We still have 2.5% in each tail, okay? But not very likely, not that likely, okay? Now look, we can show this, the regions as following. If it's a green region, if t-value, calculated t-value is inside green region, we can't reject null hypothesis because it seems like this t-value is quite common. But if we have one of the red regions, then we reject null hypothesis because it seems like t-value is too extreme. And of course, you can change the confidence level to 99 or even larger, depending on the case. Okay. So if we get back to this example, I can show you the levels. Okay, so these are the levels. So you can see that in this case, this will be rejected, right? So this will be rejected. This case will be rejected because it's this minus 3. It's not very likely. Most of the values should be between minus 2.26 and 2.26 in this case, okay? But if you take, for example, confidence level 99%, so these are rejection limits for 99% cases. So here we have 99% of most common values, right? And you still see that the t-value that for our last calculated sample will be too extreme. So we have to reject null hypothesis, okay? So now you got the intuition how the hypothesis testing works, but we don't know yet how to calculate this probability, the measure of extremeness, and that's what we are going to do in the next video.